So here we have, which of the following represents the equation for y equals root x once it has undergone a horizontal translation? So we're going from a root x function to a root x function. Can I type these into my calculator? Yes, they're both radicals. They're both radical graphs. It doesn't have an f in it, right? Remember, if it has an f in it, it's not actually a graph. It's the transformations on the graph of f, so you can't type it in. But this one you could. So here it says it undergoes a horizontal translation 4 units left, so I need a +4, so it kicks this one out and this one out. And then a vertical translation 3 up, well, it would have to be this one here says the graph of y equals f of x has been transformed to the graph of y equals f of x plus 3 minus 2. So what's happening to my f of x graph? It's being horizontally translated 3 units
Left.
and a vertically translated 2 units down, because I'm going from an f of x to a transformation of an f of x, right? Just hit that with a ponytail. I don't even know why this exists on the computer. I've never used. That doesn't look like $4. And you don't look like Margot.
She came up here.
So, we have the graph of y equals f of x has been translated 3 units to the left. Well, this is 2 units to the left, out. This is 3 units to the right, out. So now we're doing mapping, right? Well, both of these are 3 to the left. But okay. So both these are 3 left, cool. Why are these 3 to the left and not 3 to the right, which confuses people? Those are 3 to the left. But why do people want to put them +3? Yeah.
Because it's x minus k, not x plus k.
Right. So here it has x plus 3, so it's actually x minus 3, which makes us go 3 to the left. And mapping is exactly like words. I'm moving a coordinate. How do I move a coordinate 3 to the left? Well, I actually subtract 3 from it, right? And then I want to move 2 units down. Which one of these moves down? C or D?
C.
C. Okay, this one, as a result of the graph of y equals x cubed, I'm going from y equals x cubed to y equals x cubed, right? If this x cubed, let's pay attention here. So we're going to move this over. This is not an f of x, right? It's an actual cube to a cubed graph, right? Now, this doesn't exist, but what happens if this did? What if they said we were going from y equals x cubed plus 2 graph to y equals x minus 3 cubed plus 4? Now what would be my transformations? I would still be 3 to the right. 3 to the right. But what would my vertical translation be? Not 4 up. It would be 2 up. Because I already started at 2 and I'm going 2 up from there. So you have to watch yourself. If your original graph is like a graph I can type into my calculator, and the next one is a graph I can type into my calculator, I have to compare them. Where was I? Where am I? And how did I move to get there? Okay? You see the difference in where it's like the f of x graph? We're moving a coordinate. Oh, so much better. We're moving a coordinate. 327. When we move a coordinate, what do we use? Mapping. So I know it's easier right now, but we're still going to use mapping for now. So we have x plus 3. If you move 3 to the right, y plus 4. And so we get 327 becomes 3 plus 3, 27 plus 4, which is 6 and 31. And they want the y, so 31. And when we fill in numeric response, we remember that we always fill them in left to right. The partial graph of the function f of x is shown below. The range of it is f of x is greater than or equal to -11. Now I have a transformation happening because I can't type that in my calculator, right? We are talking about range. Yeah, that's an eraser. Okay, we are talking about range. What's the only thing that affects range, guys? What's the only thing that affects range? X or Y?
Y.
Y, because range is Y. We agree? So I could like put like a smiley face in here instead. 3x plus smiley face with a negative. It wouldn't matter what I do to this, right? I can put whatever I want in here because this is, I don't care about that when I'm talking about range. All I care about is what affects the range, which I'm moving it what?
3 down.
3 down, that's all I'm doing. So where's it going to?
-14.
Yeah. All right, the other side of the page we're doing tomorrow. Go to stretches. Okay. So we have talked about translations, and what translations do is they move right or left or up or down, right? And how do we translate stuff? We add or subtract to get it to move with translations. With reflections, we multiply by what? -1. So a reflection, if you multiply a y by -1, if it's negative, it'll become positive, and if it's positive, it'll become negative, so it reflects on the x-axis. If you multiply an x by -1, it reflects on the y-axis. We agree? But we're multiplying by -1. Today, instead of just multiplying by -1, which is actually the reflection, we're going to multiply by a number as well. So a number causes it to stretch. So to widen or narrow is what a stretch does, but it's still a multiplication. Stretches, however, some people will get like a -3 in front, and they'll say it's vertically stretched by a factor of -3. No, it's vertically stretched by a factor of 3. What does the negative do? It reflects it. That's why we learn it first, so that we know that, right? So there's two transformations when there's a negative. Okay, so we're going to look here. A stretch is a transformation that changes the size and shape of the graph. The original and the new graph are not congruent, so not the same. So there are two types of stretches. There's vertical, which is what you talked about last year, and then there's horizontal, which affects the x. Okay? Vertical stretches are in the form y, are in the form y equals a f of x, where a stretches the graph vertically by a factor of a, about the x-axis, it should say. So remember, if you have a negative here, it's a reflection in the x-axis, true? This is a vertical stretch about the x-axis still. Oopsies. I keep forgetting when I switch my to a different board, it doesn't point from it. The point xy becomes xay, so we would write it as xy becomes xay. So stretches and reflections multiply, translations add or subtract. So that's why you always have to do them in the form SRT. When you write out transformations, you write them in the form SRT, S-R-T. Stretches, reflections, translations, due to bed mass. Technically, stretches and reflections could be flipped and you would be okay because they're both multiplied, but you have to do translations last because they're adding and subtracting. You have to do bed mass, multiplication first, then adding and subtracting. The points on the x-axis are invariant. Why are the points on the x-axis invariant? If I'm multiplying my y's by a, invariant means doesn't change. Yeah.
Because along the x-axis, y is 0, so it doesn't matter what you multiply it by?
Correct. So on my x-axis, I have x comma 0. That's what every coordinate on the x-axis is going to be. X comma 0. The x will change every single time, but the y will not. We agree? So if I apply that to my mapping, I would get x comma a times 0, and anything times 0 is just 0. So what kind of transformation do I have to have that the x-axis wouldn't be the invariant when y is 0? What transformation would move a 0? Would a stretch? No, I'm multiplying by a number. Times 0, still 0. A translation. So only a vertical translation will actually move the y equals 0 off the x-axis, right? Because they'll move it up or it'll move it down and they'll move it off. But if you have a stretch, a vertical stretch, or a reflection in the x-axis, both of those will not move your points off the x-axis, so they'll always be invariant. Okay? So what do I mean by that? Here's a little suggestion. If I give you a graph like this, you don't have to draw this, I'm just proving a point. If I give you a graph like this, this is a degree 4 graph. If I give this to you, and I say this is f of x, and then I say my transformations are -3 f of x. That's the only thing. So the only thing I have happening to it is to the y's, correct? Nothing's happening to my x's. I have a vertical stretch by a factor of 3 about the x-axis, and a reflection in the x-axis, correct? Where would my invariant points be? On the x-axis, because if I apply my mapping would be xy becomes x, because nothing happened to my x, right? Still an x, comma -3y. what's the only thing I could input in here that the point would stay the same? A 0, correct? And where are my y's equal to 0? Here, 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 here. So they could give you that to say determine the number of invariant points, and it would be 4. Could you sketch the whole thing and then find it out that way? Sure. Or could you just reason through it? So it's way better if you actually understand why the x-axis in this case would be where it's invariant. Because if I plug a 0 in here, the points will all stay the same. So wherever my y's are equal to 0, when I have a stretch and a reflection vertically, they will stay the same. Likened to when I have a horizontal stretch and a reflection in the y, my y-axis will stay the same, right? All right. So, I really hit that plus sign a lot. Where did my page go? Guys, Bueller? Oh no, oh no. Oh, what? What the what? Oh. Hope I can go back. Come on. It's why? How did that even pop? How is it? What? Guys, help me. Where did the page go? Anyone helping? Anyone have any ideas how to fix this problem? Like what the? I'm going back a lot, guys. It's Alt F4? No. I'm not shutting down my... Okay. I don't even know what happened. I don't know. Maybe one more suggestion. Not even a blank page between them. I don't even know. I got nothing.
Control Shift Q. So wait, great. That works.
Find out print it again.
I don't know.
Okay, so we talked about stretches, and you've talked about vertical ones before. We're going to get another thing up here at some point. Awesome. I love it. Vertical stretches, you have to write vertical stretch by a factor of 3 about the x-axis. You have to write the whole thing. The only thing you can get away with not writing is the vertical part. The vertical part helps you write the rest. So I always write the whole thing. If you miss any of the other stuff or make up some words along the way, they won't give you the marks. It has to be read vertical stretch by a factor of 3 about the x-axis. Okay? That's what they'll look for in the written response, and it's what I'm going to look for too. Once I get some new notes that have that page in them. This all started poorly because of his loud TV. I blame him. You know? All right.
Did you say bird?
Wow, I deleted a few pages. All right, here we are. Okay, the points on the x-axis are invariant. If the A has a negative sign, it's a reflection in the x-axis. We've talked about this. So describe the transformations. We have to go stretch, reflect, translate. Does this one have stretch? A stretch at all?
Yes.
Yeah, what is it?
5 factor 4.
What? We're going to write it like that?
Vertical stretch.
There we are.
5 factor 4.
Vertical stretch, what?
Vertical stretch. 5 factor 4.
Uh-huh.
Oh, x.
There we go.
I didn't see any line. I didn't see anything.
About the x-axis. You're like an old married couple. All right. Sound like my husband and me. No, that's not what I said. No, you said it. No, you said it. We need like to tape record because now we're old and we can't even remember what we said. Okay. Reflection in the what?
X-axis.
In the x-axis. This is true. Now, remembering this, if for your daily quizzes or for your homework you're having to flip back to your notes every time to figure out if it's in the x or in the y, that's going to be bad for your test. You have to be able to answer these without having to cheat all the time, right? Because you don't have the notes for your test. So if you're having to look back and be like, oh yeah, it's x-axis. Oh yeah, it's y-axis. You have to, at some point, be able to release that and just know that it's x-axis or y-axis, okay? All right. We're going to flip over. So this one here, we have y equals x squared, then replace y with 3y, and graph it on the same axis. So your x squared graph is 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. And to be honest, I forgot to do this on the whole last page, like the last set of notes that we did. We always have to say what our scale is. So I'm going to say x scale of 1, which means every tick is worth 1, and a y scale of 1. Then you don't, like, you know, in science you have to label them like 1, 2, 3, 4, 5, 6, 7, 8. You label your axis all the time. You can just put what your scale is, and then they'll know what the axis is. Another fun fact. If your x scale is at 1, your y scale doesn't have to be 1. Your y scale could go up by 5 or 10 or 15. They can go up by different amounts, right? And exponential graphs will have that happen because you grow really fast as you move slowly across the x-axis. Okay, so we're replacing y. So when we replace, like we replace a tire, we take the old tire, we throw it out, we replace the new tire. So our equation is y equals x squared. We go to our old tire y, we huck it out, we replace it with 3y. What did I tell you we should always have it in? Your equation should always be in what? Minus with y equals. Y equals. There we are. That was scary. That's equally as scary as my salsa conundrum. Okay. So if I divide by 3, this isn't as helpful for having a vertical stretch, right? Because it's not blatantly obvious. Dividing by 3 is the same as multiplying by what?
1/3.
1/3. Cheers. Exactly. 1/3. And the reason you can have a 1 in front of here and it would join it and make it 1/3 too, correct? So what type of stretch is this?
Vertical.
Vertical. Because it affects the y's. And why do we know it doesn't affect the x? Some people say, well, it's with the x. No, it's not. Does this x have brackets currently? If you want to give it brackets, where does the brackets go around? Just the x, right? So my x has nothing with it. If it's a horizontal stretch, it would be in the bracket with the x, and it's not. So we have a vertical stretch by a factor of 1/3 about the what? Okay, grab out your calculators. Type x squared into your y1, and then type 1/3 x squared into y2. If you have the older calculators, you have to put the 1/3 in brackets or it doesn't know it's a fraction. For you guys, you can just use the fraction button, right? Alpha y equals alpha length. So we have x squared, and then we have alpha y equals enter, or alpha length. If you have the other ones, 1/3, or the one I have right here, I guess, x squared. So I press graph. My graph got wider. Why is that? What's happening to all my y's? What is my mapping? X, y, x, comma, 1/3 y. All of my y's are 1/3 the size. So what's it taking? It's taking all those y's and it's dropping it down to 1/3 of it. Dropping it down to 1/3 of it. Dropping it down to 1/3 of it. So it actually makes it wider. Right? So for example, -2 and 4 is going to become -2 and then 1/3 times 4 over 1. So I'm going to get -2 times 4/3, or -2 and 4/3, so 1.33333 repeating. So it's like here. And then 1 goes to 1/3. And then 0 stays 0. This one's invariant. Why is it invariant? Because y is 0, and when I multiply 1/3 by 0, it doesn't stay 0, right? And then this one will drop to 1/3. And this one is 1/3. I think you put the volume back up. Anyone else agree?
What's he even doing?
Teaching.
What are you teaching?
It's a crazy thing.
What are you teaching? Volume. Use 100
Thing.
Use it.
All right. So if we go to y equals and we put in, let's say, a larger fraction than a third. What would be larger than a third? 2/3. 2/3.
That blew my mind.
I was going 7/8, so I was impressed that you went with 2/3. I was like, well, that's so much smarter than my 1/3 conundrum. Okay, so if it's 2/3, it's actually narrower, right, than the 1/3, because I'm reducing each of those numbers by 2/3, so it's not going to drop them as low, right? So of course it's going to be narrow. It's going to be less narrow. Okay, what if I don't put a fraction? What if I actually put a number greater than 1? So those were all less than 1. So what if I go like 2x²? It's narrower than the original. Why would that be?
All the y's are multiplied by 2?
All the y's are multiplied by 2, so they're doubling in height. So if it's like 2/4, it's now going to be 2/8. Well, that's way higher, way faster, right? So if my 2/4 would be 2/8, so it's going to be up here. So I'm going to like narrow really quick, quite a bit quicker, right? So actually, the larger your a value, the narrower your graph is. And the smaller your a value is to 0, the wider your graph is. Now, why do I say to 0? Yeah.
It's like -3, your graph is still.
It's still the same wideness. It's just what? It's just flipped. It's reflected. That negative doesn't cause a stretch any more or less. The negative doesn't cause a stretch at all. The negative causes a reflection. Yeah. So between 0 and 1, your graph is wider. And then greater than 1, your graph is narrower. And the more greater than 1 it is, the more narrow it gets. All right. So this one I replaced with 1/2 y. So I get 1/2 y equals root x. Root x, type root x into your calculator. We do a whole unit on radical graphs. By a whole unit, I mean 2 days. It's literally 2 lessons. That's why there's 11 units. No, you have two lesson units, 4 lesson units. So we press graph. What? Why is there only like this half kind of looking parallel? It's kind of like rolling.
You can't have a negative under a radical.
Can't have a negative under a radical. It's true, but you can have a what under a radical, which is where we're starting at. So many answers, then quiet, like nice. Okay, repeating myself. Negatives we cannot have.
Nope.
Why does this graph start where it starts? What?
X equals 0.
Because you can take the square root of 0. That's the very first spot. Oops, spot. I want to say start and spot together, so I said smart. It's a new word. You're welcome. So when we are typing this in, we can start at 0, 0, and then we go root 1 and 1, and then root 4 and 2, root 9 and 3, right? Because you can literally just put an input and take out an output. So when I go to graph the original, we could do a t-table, like you did in grade 10, and junior high, which is square root x. So if I put in 0, I get an output of 0, because this would be the square root of 0, which is 0. If I input 1, I get the square root of 1, which is 1. If I input 4, I get the square root of 4, which is 2. Why did I not choose 2, 3? Can I not pick those? You can, they're just going to be decimals. If you want a more accurate graph, you'll pick those. You'll go root 2, you'll get your little decimal, you plot it. You'll go root 3, get your little decimal, and plot it. And your decimal is going to fall between 1 and 2, right? And then I'm going to do 9, which is root 9, which is so I have 0, 0, 1, 1, 4, 2, 9, 3. He was really thinking right now. And I'm going to label it as y equals root x. Okay? Now, this is happening. I want you to put it into y equals and give me the new graph using mapping. So, what's our mapping for this one? Well, we have to get it into y equals, how do I get a half to move? Multiply by 2. Every term. There just happens to only be one term on this side. Check this. What if it was like this instead? Y equals square root x plus 3. And I had a half over here. What would I have to do? Every term by 2. So this one by 2, this one by 2, and it would also stretch my translation, which makes sense because my translation is vertical. It stretches everything that's vertical, right? So I would actually get y equals 2 root x plus 6. And this is the error that happens that people always tell me it's 2 root x plus 3. Remember, your vertical stretch stretches all the vertical things. This is a caveat. This has nothing to do with the question. Okay, I made a totally different question. But that's when we start putting more things in and we add more things, which happens tomorrow. That's when people start making oopsies. So I wanted to bring that up, that if there was actually a translation, it would stretch that as well. It stretches all vertical things, all y's. Okay? So we have 2 root x. So all of our points are being multiplied by 2. Our x's stay the same and our y's are multiplied by 2. So 0, 0 is invariant, right? We're going to write that just to remind ourselves. That's invariant. Didn't change. And then 1, 1 becomes 1, 2. And then 4, 2 becomes 4, 4, because it multiplies by 2. And then 9, 3 becomes 9, 6. So sometimes, like when it's a parabola, it's easier to see when it's narrower and wider, right? But you're going to have more functions than just quadratics. So last year, your teacher could say, well, it widens if it's between 0 and 1, and it narrows if it's greater than 1. That works with a quadratic, absolutely, and a polynomial. But if it's a radical, it sometimes will widen it or narrow it. So you have to actually make it make sense to you. If I'm multiplying all my y's by 2, and this is the type of graph I have, and I'm pulling it, oh, okay, it's going to get taller, right? Like it should make sense rather than memorizing. And then here's the new thing. All right, let's do this. Type this into your calculator. Y equals x squared. We're going to go back to quadratic. So that's what we knew. That's what we did a lot of in grade 11. So we always are going to go back there first. So y equals x squared. I have to press that one. Graph. Cool, there it is. Now, I want to horizontally stretch it. So it has to be with the x. We agree? Like if it's outside of the x, it's vertical. If it's in with the x, it's horizontal. So we need to be in with the x. If it's a quadratic, the x is squared, right? So it needs to be in with that x squared. So I want to stretch it. So I'm not going to tell you what I'm doing. I'm just going to put in numbers. I'm not telling you how we're stretching it. So we're going to put in 3. That's an x. Lepp. 3x. You can all be scared. It's fine. Squared. So we do know this is a horizontal stretch because it's with the x. We just don't know what kind of stretch because I haven't taught you that. But it's a stretch. Okay? Press graph. Wait a tick. It didn't stretch it by 3. It's not 3 times the width. My x's aren't multiplied by 3. If my x's were multiplied by 3, this graph would be wider, wouldn't it? Like 1, 1 would become 3, 1. So it would be like here, right? It's not. It did not multiply by 3. What happened to the graph, do you suppose? So this is graph. So my red is the narrower one and the blue is the wider one. You can go in here, but it's not as optional. But if you look at the graph, it didn't widen it by 3, it narrowed it by 3, which means it's a horizontal stretch by what? What do you suppose? What guessing? Just guessing. Instead of 3, what do you think it might be? Yeah. 1 over 3. Your horizontal stretches are always 1 over the b value. So when we look at transformations, transformations are in the form this: y equals a f b x minus c or h plus d. Like, these can be whatever letters we want them to be, right? We could label it M, N, O, P. Like, it doesn't matter. So some people get really stuck. They're like, but my teacher taught me P and Q, and my teacher taught me H and K, when I can give you C and D. It doesn't matter. It matters where that number exists in the equation, right? It doesn't matter what letter goes with it. So this here is my what? We talked about this. Vertical stretch, and if it's negative, it's a reflection, and this is my K and my vertical, bless you, translation, and we talked about this. This is my horizontal stretch, and if it's a horizontal stretch, horizontal translation, it's in the opposite direction because of that minus sign, correct? We also talked, if this b in front of it, if in front of my x I have a negative, I have a reflection in the y. We talked about that yesterday. This b, though, this is a horizontal stretch by, or vertical stretch by a factor of a. This is a horizontal stretch by a factor of 1 over b. Because what it actually does to the graph is it does the reciprocal of b. We just saw that. I put in a 3 and it made it a third. Let's see. I'm going to take out the 3 and I'm going to put in, what do you think I'm going to do?
1 over 3.
1 over 3. Let's see what happens. I widened it. It multiplied all the x's by 3. So it actually does the reciprocal. Okay? So the horizontal translation is the opposite because of that minus. The horizontal stretch is 1 over b because that's what it just does to our graph whenever you put it in. So here it says horizontal stretches are in the form y equals f b x, where b stretches the graph by a factor of 1 over b. About the what do you suppose? Y-axis. Because it's making it wider or narrower about that y-axis. The point xy becomes the point xb over y. You can say it that way, or you can say xy becomes 1 over b x comma y. Basically, b is the reciprocal. And why do I say reciprocal rather than 1 over b? 1 over something is the reciprocal. Because if b was 2/3, what would it stretch it by a factor of? 3/2. It just flips it. Yeah.
Can you tell the difference between a vertical and a horizontal stretch?
If it's in the bracket with the x, it's horizontal, because it affects horizontal things. And if it's outside, it's vertical.
Okay.
So if I am given this as an equation, y equals 3x squared, is that vertical or horizontal?
Horizontal.
Vertical.
Sorry, I lied.
Because, why? No brackets. Yeah.
If you were just given a graph without an equation, how would you tell?
If you were just given a graph without an equation,
Would that be a
they would have to word it, or they'd have to give you a mapping, or they'd have to give you a transformed form, or you wouldn't know what the heck stretch out at all is. We also do talk about if we go from a graph to a graph, which is the hardest one, which we'll do on Monday. I'll give you a graph and I'll make you go to a new graph and you have to give me the transformations of what happened. Then in that case, you can use a vertical or a horizontal. You can only use one or the other. So you figure out which one's easier to use. And then if you put it back into the equation for vertical, it just is, if it's a vertical stretch by 3, it goes in as a 3. But if it's a horizontal stretch by 3, it would go in as a third. That's it. Yeah, so we'll talk about that on Monday. That's the most complicated part. Okay. Oh, and then I was going to say, sorry, if it was horizontal, it would be like this. Right?
Like, will that equal the same thing on the
No, because what would this be? I could actually put the squared through on this one. It's 9x squared. So only with quadratics can we do this. A horizontal stretch by a factor of a third is actually the same as a vertical stretch by a factor of 9. Because you can apply the 2 in, right? Now some people will do this. Okay, well I give them transformed form, and they get this. And then they'll say, oh, can I just bring that out and make it a 3? No, it's with the x, right? So I can only change a horizontal to a vertical if it's in an actual function. What do I mean by that? Well, if I gave you this, a cubic function instead. Well, this would be a horizontal stretch by a factor of a third, or I could apply it through, and it would be a vertical stretch by a factor of 27. Right? And they can use them interchangeably. but it's with functions that you can do that. This is a function, but this is transformed form. That is a horizontal stretch by a factor of a third. It can't convert it. It's just like another way of saying horizontal stretch by a factor of a third in a function form. Okay. And then the points on the y-axis are invariant, which we talked about, and then B, a negative sign in front of it, is actually a reflection in the y-axis, not a stretch. And we're going to flip over to here. To this one. So now, example 3, we have x squared once again. If you wanted to fit more points on here, you could do like 3 and 9. You just have to make your y scale be 2, right? You can fit more points on it. So now we're replacing, it says y equals x squared, then replace x with 2x. And once again, we take that x tire out, we replace it with 2x. So we're going to get y equals 2x squared. What's my mapping? X, y becomes, yes, well, close. What affects, this affects my y, so there's nothing out there that affects my y. This affects my x, it's not 2x. Nope. 1/2. It would be 4, you could do 4y, Catherine, that's what you're saying? If you wanted to, you could go x, y becomes x 4y if you had inputted the 2. You'll get the same exact graph. So this is a horizontal stretch. Am I allowed to short form any of this? Am I allowed to omit any of it? The only you could omit is horizontal. But we put it, because if you don't put the horizontal, that's actually not helpful. Horizontal stretch by a factor of what? 1/2. Do you see in mapping I use a half? Do you see in words I use a half? Remember words and mapping? Or in a heart, because you use the same thing. Factor of a half above the what? The y-axis. So if I apply my mapping, I could have -2, 4 becomes 1/2 times -2, comma 4, which gives me -1, 4. Then I can do 1, 1, -1, 1, sorry, becomes 1/2 of -1, comma 1, which becomes -1/2 and 1. Zero, 0 becomes 1/2 of 0 and 0. 1/2 of 0 is 0. So this one is what? What is this coordinate?
Invariant.
Yeah, it's an invariant point. And then I have 1, 1 becomes 1/2 of 1 and 1. So I get 1/2 and 1. And then 2, 4 becomes 1/2 of 2 and 4, which is 1, 4. Oh, why did I just change the group? Does it make sense? So it needs to make sense. If you are going, okay, with the B, I flip it. Okay, but the A, I keep it. And then with the horizontal, I flip it. And then, no, then you're going, do I flip, do I keep, do I flip, do I keep? You have to understand, right? So we put in the B. When it was a 3, it actually made the graph a third of its size, right? When it was a third, it actually made the graph 3 times its size. So your B actually does the reciprocal of what it is. and then the h or the c or whatever we want to call it, x minus h or x minus c, it's x minus, so it always does the opposite because you have that minus sign in there, right? We have to know why it does what it does, because then you won't mix them up on the test. You'll understand why, and then the errors go away. Okay, then we're going to flip over. We're going to bypass the radical. We're going to go to here. So, do you see how this one here, I have y equals 4 minus x cubed? This is my original. 4 minus x cubed. If that still exists, then no transformations happen. So if it's 4 minus x cubed and became 4 minus x cubed, nothing happens. But this one says, describe the transformations that occurred to each original function if now it's 3 times 4 minus x cubed. So this is still the same. So what's the only thing that happened? And that vertical stretch could be applied to both the vertical translation and in front of the x cubed, right? They're just not distributing it. They're just leaving the bracket and putting it in front, right? They're just not distributing it through. So it doesn't matter they don't distribute it. It's still a vertical stretch. By a factor of what? 3 about the x-axis. And if words and mapping are the same, then what's outside here affects my y's. This affects my y. So my xy will become x. Nothing happened to my x. And what? What kind of y? 3y. Because if I use a 3 in words, I use a 3 in mapping. Words and mapping are just two separate ways of explaining the same thing. Like if you ask me a question and you're like, Ms. Lepp, how do I do this? And I explained it to you and you're like, no, I don't get that. And I explained it to you in another way, which means the same thing. You'd be like, okay, I get that. That's words and mapping. This one is words. This one is mapping. They are the same way of explaining the same thing. One's just moving a coordinate, and one's just explaining it in words. All right? Okay, this one, y equals 4, so the 4 is the same. And then x cubed. Darn it, there's a 2 with it. So what is this? Horizontal stretch. By a factor of
1 over 2.
2. About the y-axis. And if words and mapping are in a heart, and I'm using a half in words, I'm going to use a half in mapping, right? The number doesn't change between words and mapping. So I'm going to get xy becomes, and because it's with my x, it affects my x, 1/2 x, comma y. Don't overthink it. Same number I use in words is the same number I'm going to use in math. Now, a catch with transformations, and this is where people get this wrong. When you state your transformations, it has to be in this form. Y equals a, let's say f, or even just the equation, doesn't matter. Then it has to be in b, x minus c plus d. I have to have a positive 1 in front of my x when I go to say my horizontal translation, or it will be wrong every single time. So before I go to do any type of transformation work, I always make sure my equation is in y equals and that there is a 1 in front of my x. If there's not a 1 in front of my x, I have to GCF first. Where does that happen? Let's look at b. Do you see b? Does it have a 1 in front of the x? No, so everyone will tell me that's a horizontal translation 4 to the left. You will tell me that. It will be on your test as an answer, and it will be wrong. You have to have it in y equals and a 1 in front of your x. So let's do that first before we even touch transformation. How do I get a 1 in front of my x if I have a -2? Just take out the -2, right? And when you take out a GCF, you're actually dividing. right? Every time you take a GCF out, you're dividing by that number. That's what a GCF does. It divides by that number. So when you were in grade 10 and that you had like 2x plus 4, and your teacher took a 2 out, what they were doing is taking a 2 out. If you take a 2 out, the reverse of taking the 2 out to put it back in is multiplication, correct? So taking it out is division. So if I go 2x divided by 2, I get x, plus 4 divided by 2 is 2. Well, if I wanted to go reverse it now, what would I do? Multiply, right? To put it back in. When you distribute, you multiply. So when you take out a GCF, you divide, because they're just reverses of each other. These are actually equivalent, right? Both of these are equivalent to each other. One's just the GCF of it, and the other one is just the full thing. So when I take that 2 out, negative 2 out, because I can't have a negative 1 in front of my x either. Take the negative 2 out, I'm left with x minus 2 squared. So this actually isn't 4 to the left, it's actually 2 to the right. And if you forget to take that out, which you will, common error 101, you're going to need to make sure you have a 1 in front of your x. So before you go, please listen and write this down somewhere in big bold writing and highlight it. It's written down somewhere in big bold highlighting. Before you go to do any transformations, make sure there are 2 things started if you have an equation. Your equation has to be in y equals, which most people will remember, and you have to have a positive 1 in front of your x. So before you do mapping, before you state transformations, before you move a graph, before you do anything, if you have an equation in front of your face, it has to be in y equals, and you have to have a positive 1 in front of your x. Now, why do I say that? Because most people will start remembering to take the 2 out. But if they're given this, they won't. They'll tell me it's 4 to the left. Do I have a positive 1 in front? Is it in y equals? Cool, yes. Do I have a positive 1 in front of my x? No. So I would have to go take a negative 1 out, and I'd be left with x minus 4 minus 7. So it's actually 4 to the right. Do you see how that's an oopsie that could happen? Most people will spot the number, the coefficient in front having to be pulled out, but when it's a negative 1, they'll just oopsie and not spot it as much. So every time you are given an equation, ever on a test, the first thing you do, okay, before I do anything, I get it into y equals, I make sure there's a plus 1 in front of my x. If you do that, you'll get rid of half of your common errors. Okay? All right, and we're here and here. I want you guys for both of these, I want you to do example 6 and 7. Both of them are describing transformations, which I want you to do, but I also want you to list the mapping, both. Transformations and mapping, just practicing and practicing and practicing so we don't make oopsies. Transformations and mapping. So this one here, we have a vertical stretch. By a factor of what? Factor of, pardon? I think I'm hearing whispering stuff too. About the x-axis. Is there any horizontal stretches? No, and sometimes it helps to actually put the x in brackets so that you see it's by itself. Like if there are no brackets, if there are no brackets around the x, then it is just the x that's in brackets and there's no transformations, right? Then we have a reflection, so we have to do CERT. Stretch, reflect, translate. So we have a reflection in the x-axis. No other reflections. And then a vertical translation. 3 units up. So we get x, y. Becomes x, it stays the same, negative 2y plus 3.
When you write the reflection, can you say reflected on the x-axis?
I do reflection in the x-axis because it's in the approved resource that is the textbook, and they can never ever give you a wrong. So if you follow for the Alberta curriculum, the approved resource is this textbook. So anything that's in this textbook, they cannot mark you wrong. And they can't like even hum and haw over it. So if we're like, ooh, I wonder if reflection in the x-axis is good. Well then we go look at the textbook and it says, oh, reflection in the x-axis. And you're like, well then, done. See, like this one even here says, copy the graph of the function and sketch its reflection in the x-axis. The moment it's written in here, they can't, it's right. Because this is the approved resource. So I would go by everything in here because it's like, you can't challenge me.
Is reflection about the x-axis is okay too?
I would do reflection in.
Okay.
I wouldn't go challenging. That's just what I'm saying. Because like, I know we have like, when we've been marking, we grab the textbook and we're like, that's not in there. Okay, well now we have to discuss it. Do you believe that reflection in, across, about, amongst, we've had that. Do you believe that that is the same? And then we have to have a big discussion, and then the head person's like, oh yeah, I agree with this one, and we make a list. We're like, is the reflection in okay? We're like, yes. Like there's no humming and hawing. This baby has been pulled out. No, no. All right. So we have a horizontal stretch. About the x-axis by a factor of what? What? What left? Horizontal stretch by a factor of. Wow, I was really writing that out of order. I was just proving that you shouldn't do that. I don't know what I was doing. Okay, horizontal stretch by a factor of?
It's still,
Two. But we went over 2.
1 over 2. About the y-axis. Then we have a reflection in the, don't all answer at once. It's with the x, it's all with the x, because it's squared. So it's reflection in the y-axis. And then a horizontal translation to units right. Now some people will say that's vertical though. It's not with the x anymore. If it is with the x, if I can do this back again. Can I do that back again and put it with the x?
yes.
Then it's with the x. That is not a vertical stretch. If I take it out, it's still with the x, right? Because I would distribute it right back into the x. So that's a horizontal, horizontal, horizontal. Vertical is when it's completely outside of the bracket and the bracket is squared, right? If it's in this bracket with the square, that is horizontal. So then my mapping would be x, y becomes negative 1/2 x plus 2 y. This one is a no stretch, no reflection. We have a horizontal translation. It's with the x. 2 units, right? Do you see how it gets more complicated when everything can be together? And then a vertical translation. One unit up. So x, y becomes x plus 2, y plus 1. Okay, before I do example 7, I have to check, is it in y equals? Yes. Is there a 1 in front of the x? Yes. Then I can carry on, right? So I have the only stretch I have is this one out here. And if it's out here, it affects the y's. If it's in here, it affects the x. So this is a vertical stretch by a factor of what? Two. Did our vertical change at all? No, it was just our horizontal that flipped. Vertical stretch by a factor of 2 about the x-axis. The cool thing about vertical, if you get it in y equals, whatever numbers are there, you'll always use. In the equation, in the words, in the mapping, it never changes. It's only the x's that change. And then we have a horizontal translation. One unit left. So I have x, y I move 1 to the left, so x minus 1, 2y. This one, it's in y equals, and I have a 1 in front of my x. Cool, I actually have nothing with my x, so these are all vertical things. I have no stretch because it's just a -1, so I have a reflection in the what? If it's with the y, it's a reflection in the x-axis, always the opposite, and a vertical translation b units down. My mapping is xy becomes x comma -1y minus b. This one, it's in y equals, and I have a -1 in front, oops, -1 in front of my x. So I have to go y equals f, take the -1 out, it's x minus 3. Do you see how it's still with the x though? So it's not a reflection in the x-axis, it's actually a reflection in the y because it's with the x. So I have a reflection in the y-axis. And a horizontal translation unit 3. You have homework. So xy becomes -x plus 3. Your homework is this. Take pages, yes, take pages 29. Same section. Number 6, 7 AC, 9, 14 AC,